We have discussed in our last classes about the vibrations of one-dimensional monoatomic and diatomic crystals. Now we will discuss about the quantization of lattice vibrations. So we know that the energy of an electromagnetic wave is quantized, and this quantum of energy is called a photon. This is an already known fact. Similarly, the energy of a lattice vibration or an elastic wave is also quantized, and a quantum of this energy is known as phonon. So this is the quantization of lattice vibration. So the energy of lattice vibration is quantized, and the quantum of this energy is known as phonon. All types of lattice vibrations in crystals comprise phonons. Thermal vibrations are thermally excited phonons. Sound waves are acoustical phonons, and excitations of the optical branch generate optical phonons. So all types of lattice vibrations is comprising of phonons, and this may vary in nature according to the sources of excitation. Optical branch will produce optical phonons, thermal excitation will produce thermal phonons, etc. Most of the concepts which apply to photons are also valid for phonons also. For example, the concept of wave-particle duality holds good for phonons too. Also, the energy of a phonon is given by h cross omega, where omega is the angular frequency of a mode of vibration. So all the concepts which are applicable to photons is can be applied to phonons also, including the wave particle duality. So if n is the number of phonons in a particular mode of vibration, the total energy of that mode is written as E is equal to NH cross omega. So the energy of a phonon is given by H cross omega, and if n is the number of phonons in a particular mode of vibration, then the total energy can be represented by E is equal to n into H cross omega, where n can be 0 or a positive integer. Since the number of phonons may change with temperature, the average number of phonons in a vibrational mode is given by the expression n is equal to, this is an approximate or average value given by 1 by exponential of h cross omega by kt, where k is the Boltzmann constant, that's the suffix b is written here, kVt minus 1. What is the absolute temperature of the crystals. So the number of phonons can be vary according to the temperature, and the average modes of vibration can be expressed by this equation. This is the total number of phonons. This the number of phonons can be increased or decreased by raising or lowering the temperature. This is quite obvious from this expression. So by varying the temperature, we can increase or decrease the number of modes of vibrations. The frequency of phonon waves may vary from 10 to the power 4 to 10 to the power 12 cycles per second. That is, the vibrational spectrum of phonon waves occupies a wide frequency range. So the frequency range of phonon vibration can or may vary from 10 to the power 4 to 10 to the power 12. So it spans a wide frequency spectrum. The phonon, being indistinguishable particles, require Bose-Einstein distribution function to describe their distribution in the allowed energy states of the system. Due to particle nature of phonons, the interaction of a phonon with another phonon or an electron may be considered as a scattering collision between the two particles. The phonon are indistinguishable particles, so Bose-Einstein statistics is applied to represents the distribution of the system. And also due to the interaction of this phonon with other electrons or another phonon, the interaction can be considered as a scattering collision between two particles due to the particle nature of this phonon. There is no direct evidence for the quantization of the lattice energy. However, the following experimental facts forcefully suggest that the existence of phonons. Though there are no direct evidence for the quantization of lattice energy, some of the facts which will explain in 2 points will suggesting that the existence of phonons. The first point is the lattice heat capacities approaches zero as the temperature approaches zero. This can be explained only if the lattice vibrations are quantized in terms of phonons. This can be explained only if the lattice vibrations are quantized. That is the approach of lattice heat capacity when temperature tends to zero. So this is an evidence. And the crystals scatter X-rays and neutrons inelastically. The change in momentum and energy during this process can be associated with gain or loss of one or more phonons. The properties of these phenomena can be determined by measuring the momentum of the energy of the scattered X-rays or neutrons. So what this point says is that the crystal can scatter X-rays. X-ray diffraction from crystals. So the crystals scatter X-rays and neutrons inelastically. Thus the change in momentum and energy during this process can be associated with gain or loss of one or more phonons. The properties of these phonons can be determined by measuring the momentum and energy of the scattered X-rays or neutrons. So this is also an evidence for the energy of the quantized energy of phonons. So now we will talk about the momentum of phonons. Physically, a lattice phonon does not carry any momentum, but it interacts with other particles and feels as if it has a momentum h cross k, where k represents the wave vector of the phonon. So actually the lattice phonon does not possess any momentum, but it acts as it possesses a momentum h cross k, where k represents its wave vector. Also from de Broglie relation we know that P is equal to h by lambda, where P is equal to h cross k. It is apparent that a phonon of wavelength lambda causes a momentum h cross k. So the quantity h cross k is sometimes called the crystal momentum. The physical significance of h cross k is provided by the momentum conservation laws in crystals. So the importance of this crystal momentum is provided by the momentum conservation laws in crystals. The wave vector conservation law for elastic scattering for Bragg's diffraction of X-ray photons from crystals is given by k prime is equal to k plus g vector, where k and k prime represents the wave vectors for the scattered and incident photons respectively, and G is the reciprocal lattice vector. The conservation of uh, this this equation is obtaining from the Bragg's law in the reciprocal lattice. You will study this topic in detail in the first module. That is, uh, this is a note from your first module. So here we will explain Bragg's law in reciprocal lattice. From this topic, this relation comes out, that is K prime is equal to K plus G, where K and K prime are the wave vectors corresponding to the incident and scattered photons. Okay, and G represents the reciprocal lattice vector. Okay, now the conservation of momentum and energy yields the conservation of momentum equation give H cross K prime is equal to H cross K plus H cross G. And this is for incident photon, and this is for the this is after scattering. This is a scattered photon, and this is for the lattice. And for the energy conservation, the equation H cross omega pH represents photon, and H cross omega prime. Here omega prime is that of scattered one, where omega pH and omega pH prime are the frequencies of incident and scattered photons respectively. In this process, the crystal as a whole recoils with a momentum minus H cross G, and the frequency of the incident photons remains unchanged. That is, omega pH remains omega pH prime. This also follows from the relation K prime, mode value of K prime is equal to K, which holds good for X-ray diffraction. This will clear from the X-ray diffraction from reciprocal lattice. Such a process in which the frequency of the incident photon is the same as that of the scattered photon is called normal or N process. Such a process is known as N process. N process. Consider now the case of inelastic scattering of photon, which proceeds with the emission of phonon of wave vector K, as in figure A, this figure. So this is an incident photon, and this is a scattered photon, and this is a phonon. So consider the case of inelastic scattering of photon, inelastic scattering of photon with the emission of a phonon, of wave vector K. So this is the case. The wave vector conservation law then takes the form. So the wave vector conservation law can be written like this. That is, K prime plus K is equal to K plus G. That is the wave vector after scattering. That is, K prime plus K is equal to K plus G. Accordingly, the momentum and energy conservation laws can be written as, this is for momentum, H cross K prime plus H cross K is equal to H cross K plus H cross G. Now the energy expression can be written as H cross omega pH prime, that is the energy corresponding to the scattered photon, plus H cross omega, this is the energy of phonon, is equal to H cross omega base, that is energy of incident photon. This is the energy conservation equation. Omega is the frequency of phonon generated in case a phonon is absorbed in the scattering process, as in figure. So this is the case of phonon emission, the process in which a phonon is emitted by the scattering of the photon with the lattice. In this case, a phonon is absorbed. So what will happen? the conservation laws can be written as K prime is equal to K plus G. That is K prime. This is K prime is equal to K plus G, and the momentum of energy conservation laws becomes the energy momentum equation can be written as H cross K prime is equal to H cross K plus H cross capital K plus H cross G, and energy correspondingly energy conservation equation becomes like this. From 36 or 39, this is equation 39, and 36 is the just previous energy equation, this one. From these two equations we find that omega pH prime not equal to omega pH, because these two equations, from these two equations, if we look at these two equations, we will see that omega pH prime cannot be omega pH. Such a process, that is the frequency of photon after scattering and before scattering, cannot be equal. It changes after scattering, and such scattering is called Enclave Scattering or U process. You might have heard this word when we were discussing the heat capacity, or yes, in the free electron theory chapter. In this process, a photon is created or absorbed in addition to the Bragg's reflection, and the momentum is transferred to the crystal as a whole. So, what happened in this process is that a photon is created or absorbed in addition to the Bragg's reflection. Bragg's reflection is X-ray deflection or photon reflection from the crystal lattice, and the momentum is transferred to the crystal as a whole. So that's what's happening in this type of processes. Okay, so this is about the scattering. Now the inelastic scattering of photons by phonon. So in the inelastic scattering of a photon by phonon in a crystal may result in the creation or absorption of phonon, which you have seen now. The photon-phonon interaction occurs due to the change in the local concentration of atoms, and hence in the refractive index of the crystal. So the photon-phonon interaction occurs due to the change in the local concentration of atoms, and hence since the local concentration of atoms changes, the refractive index may vary. That's why the refractive index affects when the local concentration varies. That's how the relation comes. So this photon-phonon interaction takes place when the local concentration of atoms varies. So conversely, we can say that the electric field of the light wave induces mechanical vibrations in the medium, and hence affects its elastic properties. So the electric field of the light waves or optical wave or photon induces mechanical vibrations in a medium, and hence affects the elastic properties of this wave. Now, for this, consider a photon of frequency nu is equal to omega pH. pH means for photons omega by 2 pi. This is a frequency, and wave vector k propagating through a crystal, which is viewed as a continuum of refractive index n. So suppose a photon of frequency nu and wave vector k is propagating through a crystal, so which having a continuous refractive index n. Then we can write omega pH as Ck by n, where C is the velocity, K is the wave vector, and n is the refractive index. Or this will become 2 pi nu because omega can be written as 2 pi nu. So this is Ck by n. And K is 2 pi by lambda, so that lambda nu become C by n, where C is the velocity of light. If this photon interact with a phonon, suppose this photon interacts with the lattice phonon. As a result of this interaction, the wave vector and frequency of the photon change to K prime and nu prime respectively. So by the interaction of this incoming photon with the lattice phonon, its wave vector changed to K prime and frequency changed to nu prime respectively. If a phonon of wave vector capital K, this is the wave vector, capital K is the wave vector of the phonon, and angular frequency omega is created in this process, the conservation of energy and momentum gives omega pH plus h cross omega h prime plus h cross omega. Suppose due to this interaction of the photon with the phonon, a phonon is created during this process with omega as its angular frequency and omega is its angular frequency and k as wave vector. We can represent the energy and momentum expression like this: h cross omega, this is the energy of photon, and this is the energy of the photon after interaction plus the energy of the phonons create. And the energy expression is the momentum expression is like this. This is for incident photon, this is for photon after interaction, and this is for phonon. This equation has been written without taking into account the phenomenon of Bragg's diffraction along with that of scattering. So we have not considered the Bragg's diffraction process here. Taking Vs as the velocity of sound or the velocity of phonon and assuming it to be a constant, we can write omega as Vs into k. So if we take the velocity as constant, we can write this as the omega as Vs into k. This is okay. So the wavelength of the emitted phonon, is comparable to the wavelength of the incident photon, whereas its energy is only a small fraction of the incident photon energy. So what this tells us that the wavelength of the emitted phonon, so we have seen that a phonon is emitted in this process and the wavelength of this phonon is comparable to that of the incident photon, whereas its energy is only a small fraction of the incident photon energy. From equations 40 to 43, we find that 40 to 43 means these equations. This is equation number 40 and this is 41, 42. This is equation number 43. From these equations, we find that since Vs is very much less than C, where Vs is the velocity of sound or phonons and C is the velocity of light, since this is very much less than C or C by n, since Vs is equal to this lambda V is the C by n. Omega pH is very much greater than omega. That's how we can say that the energy is only a small fraction of the incident photon energy, but it's not in the case of wave vector. It is comparable, so that the momentum is comparable, but the energy is different. It's only a small fraction of the incident photon energy, since omega pH is very much greater than omega. It therefore follows from equation 41 to this 42 that omega pH approximately omega pH prime and k approximately k prime. The wave vectors k, k prime and capital K are related to each other as in figure B. This is the figure. From figure, k is equal to k prime. This we have got here. The triangle becomes isosceles. K is equal to k prime means this is k and this is k prime. These are equals, mean this is an isosceles triangle, and we can have k is equal to 2k sine phi by 2. This angle, the angle between these two vectors is phi, and for this angle and this angle is phi by 2 and this angle is phi by 2. Therefore we will get we can write k as 2k into sine by 2k sine by 2, which means what we are doing is we are this is k vector, this is k vector. We are dividing this k vector into two halves by this line, so that this angle becomes phi by 2 and this angle becomes phi by 2. So this angle will give you half of this length and this will give you half of the length. So 2 times this value will give you k. That's how we are getting this equation k as 2k sine phi by 2. Okay, where phi is the angle between k and k prime. Thus f phonon is produced when a photon is scattered inelastically at an angle phi by 2 from the direction of incidence. So what does this mean? A phonon is produced when a photon is scattered inelastically at an angle phi by 2 from the direction of incidence. The frequency of the phonon is given by the expression omega is equal to Vs into k, where we are substituting k from this equation 2k sine phi by 2. So we will get 2 Vs into k sine phi by 2. So this is nothing but 2 Vs omega Phn by c sine phi, but we are substituting for this k value. This the phonon have been generated in quartz and sapphire in the microwave frequency range by scattering the visible light produced from an intense laser source. The observed shift in frequency of the photon agrees well with the shift calculated from the above equation using the velocity of sound determined by ultrasonic methods at low frequencies. So these are experimentally verified, that is the shift is just as that we have calculated by this expression, and it is observed in the quartz and sapphire crystal when a light wave from the or visible light from a intense laser source is passed through such crystals. So these are about the energy quantization and the scattering of photons by the phonons. Either an emission or absorption of phonon is taking place when a photon is scattered from a crystal lattice.